This is the Applied Statistics in Healthcare series, and this is the sixth and last session of the Multiple Linear Regression course. In week 6, we're going to look at a case study. Our third case study is on intervention studies and causal models. We'll cover, for the intervention study, the COVID-19 ICU bed utilization after the vaccine began. And in our last study, we're going to do an intervention study in the differences in differences study design. We're looking at the minimum wage laws and employment rates. And this is from the study that won, that was partially what won the 2021 Nobel Prize in Economics for David Card, Joshua Angrist, and Guido Embens. So let's begin. Okay, for case study 3, this will cover intervention studies and causal models. We'll look at COVID, the vaccine, and hospital utilization, as well as minimum wage laws and unemployment rates. Our first study is on the COVID vaccine. We're going to look at the proportion of adult ICU bed utilization rates by COVID patients before and after the COVID vaccine was introduced. And for the COVID study, we're looking at the adult ICU bed utilization after the vaccine in 2021. In this case, the vaccine is the intervention. We don't have records of which patients took the vaccine, so we can't call it a vaccine effect, but we are looking at the era after the vaccine was introduced, which may also include generally improved treatments after a better understanding of COVID. We will use state-reported hospital data in the U.S. between January 2020 and August 2022. Our model is the adult ICU bed COVID utilization variable equals month plus region plus vaccine. Our model is the added effects of month, region, and the vaccine era. And then from this analysis, we might ask ourselves, what other outcomes can we use with the same model? We know there are many different things that the vaccine could have impacted. We might say the vaccine has a better impact for certain things, but we can begin to test those to see how this model of month plus region plus vaccine can help explain that phenomena that we're interested in. And in this slide, we're going to look at our model results. Again, we used adult ICU bed utilization as our outcome, and that's defined as the effect of the vaccine plus the month plus the region. And overall we see the model fit is okay, but not great. R-square has a small effect size, and the intervention effect seems odd. Here's our R-square in the top right. It's 0.10. And then below that, towards the bottom of this table, we see the individual effects in our regression output. We start with the intercept. We have the month. We have different regions in the U.S. And then we have our vaccine effect. And from this, we see that rates decrease each month. For every additional month, which is the second row in this bottom table of results, for every additional month, utilization rate significantly decreases by 0.0048, and that's a significant effect. P is less than 0.0001. And how we can interpret the region effect is that region utilization rates significantly vary. P is less than 0.0001. Can be lower or higher than the Midwest reference region. And so we see in the region we have 5 rows. We have 6 regions, but we have 5 rows of coefficients. So that indicates that the Midwest region, which you don't see here, is used as a reference group. So if we look at this top effect for region, that's the northeastern part of the U.S. When we look at that compared to the Midwest, the northeastern region has a lower effect size, and that's by 0.04. So in each of these 5 rows, we have 5 comparisons with our Midwest region. Overall, we definitely see a significant difference between regions, and we can interpret for the vaccine that utilization rates are significantly higher after the vaccine was implemented by about 0.0156 points, and that's again very significant with the p-value less than 0.0001. All effects are significant after controlling for other predictors. But again, that since we have an effect that shows an increase in ICU bed utilization rates, it is counterintuitive that the vaccine would be associated with higher bed utilization rates. And in this slide, we see that the vaccine effect increases utilization, which is counterintuitive. So maybe we should consider another model. And in this graph, we see that we have a vertical dashed line at the value of 0. And that vertical dashed line at 0 indicates that there's no effect for our different predictors. These blue bars with red dots in the middle represent estimated effects, and they are the blue bars are the 95% confidence intervals. So when we have blue bars to the left of that vertical dashed line, those are effects that are associated with decreased rates, while the confidence intervals to the right of that dashed line are effects that are associated with increased rates in our bed utilization outcome. And circled in red, we have the vaccine effect. Again, that looks like a counterintuitive effect that we're going to see after the vaccine came out, that we'd see higher ICU bed utilization rates. And just to describe how each of these graphs, how each of the confidence intervals in the graph are created, they show the effect when going from the 25th to the 75th percentile in continuous predictors, or going from a 0 to 1 in a binary predictor, or the most common category to other categories. So for the region, because the South has slightly more data than the other regions, it's that reference group that we discussed in the last slide. And these different regions are compared with the ICU bed utilization rates for the South. So something that we should begin to consider is what might give us those counterintuitive results. Is there something that we're missing from our model? We discussed confounding in the previous weeks. Maybe there's something that affects our outcome, or maybe there's something that we didn't implement in our model. Maybe there's an assumption that we should consider relaxing, such as linearity. We see here in this slide, we're looking at smooth trend lines for adult ICU bed utilization by U.S. region. We see that for the 6 different regions, there are surges in ICU bed utilization that coincide with surges in COVID cases. There is a very non-linear utilization trend by month. So for what we know is that with multiple linear regression, it's trying to fit a straight line trend when we assume that there is linearity between our predictor and our outcome. However, what we do see here is that we had surges, which remember happening during the winter or the summer, and so we don't in this data we don't naturally expect to see a linear trend in our infection rates. We know that they went up and down throughout the year, so it may help us to relax the assumption of linearity, and that may be a key improvement in our model to help us get more accurate results. And so in these results, we see that there is model improvement after relaxing assumptions of linearity and additivity. In this, we relax that linear trend that we had in our first model, but we also saw that there were big differences between regions, and we can see that in these lines here. There isn't one line on top of the other. We have, for certain regions, they have higher rates, and it seems to happen at certain times of the year. So for this, we relaxed two assumptions: the assumptions of linearity and the assumption of additivity. So in other words, we're going to use, we're going to allow for nonlinear trends, and we're going to allow for differences between regions. And the way we do that is to use what's called an interaction term. And so when we look at this model formula, adult ICU bed utilization defined as a nonlinear month, and that asterisk represents the multiplication term. So we have month times region plus our vaccine. We're going to try to use that information about the differences between regions as well as the differences in the trend over time. And we see that the significant interaction shows the region effect on utilization rate is dependent on time and months since January 2020. And on the right side, on the top right, we see our R-square increase from 0.101 to 0.313. The substantial increase in R-square by 0.212 has a medium effect size, according to Cohen's book. So that's a big jump. It basically tripled by adding in a nonlinear and interaction term in our model. So that means that we don't really have that that incremental increase in our trend that we had, that our model was defined as in that very first model. Instead, what we do have is just surges or cycles, and so it would make sense that we include regression terms that account for those two occurrences of nonlinearity and an interaction between regions over time. So we benefited from modifying our model, and we have an R-square that is now triple what we originally started with. So now we'll again look at the model summary, and we'll look at vaccine first. We see that the vaccine effect now shows a decrease in the utilization rate. So we do see that over time, since the vaccine, it's helped to reduce the adult ICU bed utilization. And that's one of the things that when the vaccine came out, that a benefit that was expected was that it'll prevent patients from getting very sick. Patients may still contract COVID. However, the COVID vaccine should help our immune system fight it off, so it never gets, or so it hopefully doesn't get to the point where it's very serious. So if we're going into the adult ICU department, that indicates that our condition's gotten very serious. So if the vaccine has helped, it should help reduce our adult ICU bed utilization rate. And it appears that we have some evidence that it did help. And then when we look at the regions, we see a wide variation in regional rates, and the Southwest has the highest utilization rate. So the South probably had the second highest rate after controlling for our different predictors, but the Southwest is one that seemed to be having a higher bed utilization rate as time went on. And now we're going to look at variable importance, and we see that the most important predictors on our outcome have dots furthest to the right, and they're also the bottom rows. So we see the vaccine period had a significant impact on the outcome, but it's clear that we've seen changes over time, and there is a different picture in different regions. So the vaccine at the very top shows that it's a very significant predictor. On the far right, we see that p-value, and that's the probability of being wrong about our assumption that we're actually seeing something in our data. And we see that probability is very, very low. It's lower than 0.000. And although that's a very important predictor and supports maybe our hypothesis, we do see that there are stronger predictors. The month by region interaction is very significant, and then the differences between regions also is very significant. And but we do see the biggest impact seems to be over time. So we are seeing differences between regions and a different picture over time. And now we'll examine the partial prediction plots. These show trend lines while holding other predictors constant at their average value. And we'll start with on the left side, we're going to look at the month trend, and we see the trend looks substantially different in 2022. So our rates seem to be high. Our ICU bed utilization rates seem to be higher in 2020 and 2021, and we're starting to see some decreases in 2022. And then in the middle, when we look at the effect of the region, we see that regions definitely vary. And when we look at the effects of the vaccine era, we do see a vaccine era effect where in this model we see that the bed utilization seems to be coming down. And so now we might wonder are there other outcomes that we can use to test with our model? For this first outcome, we're going to look at the percent of COVID patients. We have a model R-square of 0.174. Trends resemble the ICU model that we just reviewed, and the effects after the vaccine started may have less of a direct effect on this outcome. On the top right, circled in red, we see the vaccine effect, and this resembles what we saw in our first model. We actually, in this data, the vaccine seems to show that there is an increased bed utilization rate associated with the vaccine, and that again is we would think it would be counterintuitive. We again see a counterintuitive vaccine effect, but this time it's in our improved model. So we have the interaction terms that helped triple our R squared in the last model, as well as the nonlinear term. We can probably improve the model by controlling for the Omicron period. So that could help our model to take into account the really big surge that we had after the variants came out. However, maybe this isn't the best outcome for the for this model. Our outcome may not fit these predictors, or the other way around, our predictor may not fit the outcome. In other words, there may be other things that we should take into account that would tell us about the effect of the vaccine. However, maybe this is one of those things where the vaccine may not have the impact that it did on the adult ICU bed utilization. Again, the ICU bed utilization is the would come from our most serious COVID cases, and the COVID vaccine had the potential to help reduce the impact of our most serious COVID cases. So while it might help to give us a better shot and not allow us to get as sick as when we would need to go into the ICU, it may not have that same impact on the percent of COVID patients. So this might not be the right model for that outcome. And now we're going to again look at the model for ICU utilization doesn't work well for deaths. So if we use deaths as our outcome, this model only has an R-square of 0.01, and the vaccine not having as strong of an impact in the area of deaths, that doesn't mean that it doesn't help. In this graph that we have in the center, we see that the mortality rate associated with COVID has gone down each year. So we do have evidence that there has been improvements over time. However, these improvements might be due to treatments in our hospital, other advances. So we may not expect the vaccine to have that big, have the same type of effect that it did with ICU bed utilization. We know that we've improved how we care for patients and how we've been able to reduce mortality over the last few years. So there could be many other things that are going on at the same time. We would expect the vaccine could help in this area as well. That we have face validity for that, but we also probably do need to take into account the different types of advances in treatment or different interventions that we've seen come out since 2020. And we see that there are significant ANOVA results, and that's the graph that we're looking at, the tables within the graph. The p-value is on the right side, and that's far lower than 0.0001. This also reflects other uncontrolled variables like advances in treatment, etc. Okay, so for this, now we're in our second study, and this is the minimum wage laws and unemployment study. We'll look at interventions, study design, and the Nobel Prize. And the technique that won, or the method that won the 2021 Nobel Prize, comes from the differences in differences study design. And in this graph we see on the left side, we have the differences in differences estimation, and we have a graphical explanation on it. And as a summary of the method, we compare trends between the treatment and intervention groups and the control group, pre and post intervention. So in the graph, the red line represents our intervention group, and the green line represents our control group. And so what we're going to do is we're going to look at the trend before and after the intervention was implemented, and we're going to see if there was a change after we started our intervention. And we can see both lines. The blue vertical bar represents when the intervention started, and we see that before the intervention started, we had similar trends between our intervention and control group, and we see that our intervention group actually had a higher rate. And so we don't have to have each group starting at a different rate. In a hospital system, you'll have most likely many, or at least a few hospitals. And so maybe interventions were implemented at one of the hospitals, or some of them, or half of them, while not implemented at other hospitals. So those would be your intervention and control groups. And we see that pre-intervention, they do show some improvement. Those rates are going up for both groups. And to the right, we see how those trends look after the intervention's been implemented. So that red dashed line represents what the intervention group would look like if we didn't have that intervention. If they were just to continue that same trend, we'd expect to see a parallel trend with our control group, and the space between the red and green lines would represent that difference in their outcomes. But since the intervention was implemented, we see that red line with a steeper upward trend, and that difference between that solid red line and that dashed red line, which is also called the counterfactual, and that represents what would have happened if there was no intervention. That difference between those two lines at that post-intervention period represents the intervention effect, and that's what we're trying to measure. We're trying to see what that shift in our intervention group's trend looks like after we implemented the intervention. And the reason we look back at the post-intervention is so that we can get an idea of what could have happened. So if we know what the pre-intervention trend was in that red line before, to the left of that blue vertical line, that gives us an idea of where we could be at if we had no intervention. And then once you have that value, then you can see what the intervention effect, and you see there was an improvement in this graph in that increase, or the intervention effect tells us how much of a benefit that intervention was. If the trend changes substantially after the treatment begins, it's supportive evidence, and we see that here. Trends can begin going up, down, or flat. The shift in trends is key. So we have two graphs going upwards, or we have two lines going upwards in this graph, but sometimes, as we know, lower values are better. So if we had two trends going downward, that's okay. Or if they were flat prior to the intervention, we would again just look to see what the shift in trends is. And here's an example of what we might see in hospital data. We're looking at hospital satisfaction ratings after the intervention was implemented at the 4th month. So we have a similar graph. In purple, we have the trend for our intervention group. In orange, we have the trend for the control group. We're looking at hospital satisfaction, and we see the hospital satisfaction rate significantly increase after the intervention started. So for the first 3 months, they both have similar rates of about 3.5. After the intervention is implemented, we see the intervention group have average satisfaction ratings go up by a whole point. It went up from 3.5 to 4.5 points, and then remain consistent over time. So that would show that there is an intervention effect, and you can see that graphically here by that shift in that intervention line. It increased during the same period that the intervention was implemented and remained constant at that rate. And so now for our study, this is the study by Card and Kruger, and this is the study that this is the work that won David Card the Nobel Prize, he shared the prize in economics. And to my knowledge, this is the only regression that's ever won the Nobel Prize. It's a simple but powerful method, and it uses everything you've already learned in the past 6 weeks. So here's the background on the study. In 1992, New Jersey raised its minimum wage from $4.25 to $5.05. A counter-argument to raising minimum wages is that the added cost will force employers to hire less people or lay off employees. Card and Kruger compared full-time equivalent rates between New Jersey and Pennsylvania to see if rates changed. Their conclusion was that we find no indication that the rise in the minimum wage reduced employment. This novel approach, comparing control and intervention groups pre- and post-test, won them the 2021 Nobel Prize in Economics. Their analysis was strengthened by a difference in differences design. To learn more, there's a link here where you can read the press release. And for our data, we see that the intervention group is New Jersey. This is where the minimum wage increased. For our control group, it's Pennsylvania. There was no minimum wage increase. Our sample is 820 rows. There are 410 fast food restaurants, and we have both pre- and post-test survey data for each restaurant. Our outcome is the number of full-time equivalent positions at each store. Our predictors are T, and that's the pre- or post-intervention period. The variable treated, and that's the treatment intervention group or not. The treatment intervention group is New Jersey, and the control group is Pennsylvania. And for our model, it's the interaction is our key predictor. Our model is T plus treated plus T times treated. T times treated is our interaction term. And here are our model results. On the right side, we see values for the intercept. The FTE intercept would be 19.9487. Our effect T has a coefficient of negative 2.4065. Our treated effect is negative 2.8835. And our key predictor is that interaction between T for time by treated, which is our intervention control group factor. And on the right side, we have our p-values. We see that T has what we would call a marginally significant. It's not significant because it's less than 0.05, but it's somewhat close. Treated is significant, and our T by treated interaction is not significant. That's the p-value is 0.0708. It's important to note that not all predictors need to have significant effects to support our hypothesis. So the a non-significant and positive interaction term shows that employment didn't decrease after the minimum wage law. In fact, it got higher. So when we look at that bottom coefficient, that interaction of time by our treatment group, we see that the coefficient is 2.91. So in fact, our employment rate in New Jersey increased, while the employment rate, the full-time equivalent rate, decreased in Pennsylvania. So let's review what these different coefficients represent. For the intercept, that is the baseline average. For T, that's the time trend in our control group. Treated is the difference between the two groups pre-intervention, and our interaction T times treated, that's the differences in changes over time between groups. And that was our main question. What is the difference in changes over time between groups? And here's a graphic display of that. We have our full-time equivalent employment rates before and after the New Jersey minimum wage law in 1992. That green vertical line represents the period when the minimum wage law was introduced. We see that in our differences and differences model, it's the difference between each group's pre and post test difference. We'll want to know if that's significant. And for our interaction, it's and how we calculate that effect size for the interaction. It's the post-intervention time for New Jersey, and that rate is 17.57. We subtract the pre-intervention rate of 17.07, and then we now subtract from that the difference between Pennsylvania at time 2 minus time 1, so it's 17.54 minus 19.95. And this is the actual calculation. So we're looking at what is the difference post-intervention for New Jersey compared to Pennsylvania. So as you can see, New Jersey's rates increased while Pennsylvania's rates decreased. So the difference between those two would show that there was a bigger impact, a positive but not significant increase for New Jersey. And we have our variable importance, and we see that for interactions, the interpretation of the main effect takes on a different meaning than in the non-interaction model. Here, T is the effect of time when treated equals 0, rather than just the effect of time in non-interaction models. In other words, T is the time trend in the control group. And if you're in the control group, your value for treated equals 0. And the interaction term, well, let's go straight to the treated term. The treated is the effect of the intervention when T is 0. Above, T is the effect of time when treated is 0. But here, treated is the effect of the intervention when T is 0. Treated is the difference between groups pre-intervention. On the average, New Jersey's rate was 2.88 FTE, significantly lower than Pennsylvania's rate prior to the intervention, controlling for all other variables. And for our interaction, that represents the added effect to the post-test rate in the intervention group. In other words, the wage increase didn't raise unemployment, and it seems it may have actually helped employment. And we can see that again. We see New Jersey's rates increase while Pennsylvania's rates decrease. And the difference in those very different trends comes out to a positive coefficient, but not quite significant. For this, we would have been happy as long as that wasn't statistically significant and negative. So if this coefficient was negative 2.91 and not significant, that would still provide us evidence that the minimum wage law didn't hurt employment. If that was significant and negative, if this was negative 2.91 and this p-value is less than 0.05, then that would have actually supported the argument that increased minimum wage law rates can increase unemployment. So for this to be that much different than some people argue, that would suggest that the minimum wage law didn't hurt employment rates. And in summary, there was no significant difference between the changes in trends for New Jersey and Pennsylvania. In fact, New Jersey employment rates were higher. The minimum wage law was passed prior to the recession in 1992. Both New Jersey and Pennsylvania were subject to the same economic conditions. The interaction term in the regression model helped show the law didn't seem to impact New Jersey employment. This causal modeling approach provides more valid results because of two methods used in the design. First, we have pre and post test, and secondly, we have control and treatment groups. The preferred approach is multiple regression, even when outcomes are binary like those in logistic regression. And oftentimes in our own work, we may ignore that pre-intervention period, and we can see that everything to the right might fit some of the things that we would just naturally want to do. We'd want to look at the most recent year's data, but if you can, it really does help to go back further in time to grab the data prior to when that intervention started. That means that you might need to go back more than 1 year. You might need to go back 3 years or even 5 years, and in some cases much more than 5 years. Hopefully we're going to be involved in those studies before these interventions have gone many years, but going back to get data prior to that intervention strengthens your study. Now you're using a pre-test, post-test. Oftentimes we may not even have a control group and a treatment group, or we might just have one medical center's data and not have that pre-intervention. But we do have an example with in the healthcare system where not using that pre-intervention data could be an issue. We see that not using good methods led to, in 2013, the U.S. Supreme Court leaving intact the award to KP for $142 million against Pfizer about off-label benefits. So Pfizer had suggested using Neurontin for multiple conditions. They showed that there were improvements in these various outcomes over time, but they didn't have pre-intervention period data. They just had that post-intervention period. So everything to the right of this vertical green line, that was the data they were showing. But the issue was that those outcomes in their hospitals were actually improving anyway. So if you didn't know that pre-intervention KP's hospitals were already improving in those outcomes, because that wasn't discussed, there was confusion and false claims that the Neurontin could actually benefit off-label conditions, and that case actually went to the Supreme Court. So there's a big benefit in using different research design methods or study designs to help strengthen your study. So that was it for our case study. I just want to cover purposes and strategies for regression in our conclusion. For purposes, regression gives us an idea of what trends exist between our outcomes and important variables. Learning about these trends gives us more accurate information. The alternative is to assign the average outcome to everyone in future data. For example, the expected average length of stay is 3 days for everyone, regardless if they are men or women, young or old, sick or healthy, etc. This can be inaccurate and unhelpful in future work. Regression allows us to test hypotheses, measure effect sizes, and do predictive modeling. For example, we may find sex, age, and health status as significant predictors, and we learn men over 65 Yours have twice the length of stay as women under 65 that are being treated for certain conditions. And everything that we've covered in the last 6 weeks is in this slide. It's regarding regression strategies. This slide shows the optimal range of improvement in validated R-squared from various methods in healthcare studies. So we have all our different methods that we covered that can help improve our model. We have that on the left side, and then we have a sort of an anticipated range of improvement by implementing these different methods. So we'll start out with our standard model, and if we include these different methods, we might see, or these different strategies, we could see an increase in our R-square. For example, for number 1, if we use valid predictors, that could increase our R-square by as much as from 0 to 0.50 in our R-square. And that's really, if we research the study, if we talk to clinical experts, we can gain a lot of information on what things we should include in our study. And this is probably the best way to help any type of model. For regression, we're doing the statistical analysis, but it's really testing to see what our conceptual model, how predictive of the outcome it is. So we really need a good foundation in that model, and by just researching the study or getting an expert's opinion, that could really improve our model a lot. And for example, the one example that always comes to mind is that back in the late 40s, the Dahl and Hill, the researchers who found the link between cigarette smoking and lung cancer, they were considering looking at automobile pollution as a competing cause for lung cancer. So imagine today not including smoking as one of the predictors in something related to cancer or lung cancer research. So valid predictors probably will have the biggest impact, and an example of that is found on slide 119. We would also look at study design, which we just discussed. That can improve your model by up to 10 points, and the slide number is 187. And then we have different things such as nonlinear terms and interactions, or both. And that R-squares to the right, as well as examples in different slides. Increasing your sample size can definitely help. And but we wouldn't want to over-exaggerate that. Sometimes if you have a big enough sample size, everything will look significant. So we don't want to overemphasize that, but it can help if you have a very small data set. Increasing the sample size can give you more accurate coefficients. And we have the anticipated increase in the R-square and an example slide next to that. Imputation. If we have a lot of missing data, also related to your sample size. But if you have a lot of missing data, we wouldn't want to lose that information in that data, even though much of it could be missing. Professor Frank Harrell calls it throwing away data if we don't use imputation to get more accurate results. And then we can also use data reduction techniques, for example, clustering or principal components analysis. That'll help. And we have our anticipated increase in our R-square and an example slide next to that. Top coding, we did that for our cost model. And we can also do it for other skewed outcomes, such as the length of stay. And then we also have at the bottom model approximation. The range reads as 0.95 to 0.99. And that won't that won't increase your R square by that high of a value, but instead it will give you a model that has an approximated R square that is about 95% to 99% of your gold standard model. So, and you can do that by reducing the number of predictors. So with the much more parsimonious model with fewer predictors, you can retain about 95 to 99% of your full model's R square. And note, it's important to note these important methods are applicable in various regressions. For example, logistic. All of these techniques you can again use in various types of regression. You're not just limited to an ordinary least squares regression like we've covered. It's also important to note that multiple strategies may or may not increase performance because of overfitting and unreliability in future data. You can see slide 141 to take a look at an overly complex model and the issue with small samples. Cohen defines cutoffs for small, medium, and large R square as 0.02, 0.13, and 0.26. R square for individual predictions. That's when you're doing predictive modeling, you should shoot for an R square of at least 0.0 or at least 0.70 or higher. And if you don't have that, you can still, if your R square is over 0.26, you can still make predictions on important groups, not individuals, that you would do if your R square was greater than or equal to 0.70. But if you wanted to make predictions on important groups, then with an R square of about 0.26 or higher, and that's what Medicare does, you can use predictions that way. And the rest of this, the PowerPoint is our appendix. And so I will show you the Card and Kruger study. I'll just show you how to do it in the I'll show you how to do it in my GUI. So I've loaded the data. I'm going to go to the model builder page. I'm going to enter the data set. The outcome is FTE. The predictors are T and treated. And what I want to show you especially is that how to do the interaction term. At number 14, I'm going to change that plus sign to an asterisk, which indicates multiplication. I'm going to turn number 13 to yes. I'm going to go back and I'm going to run the model. And then from that, we can see that we have the same model results. Okay, and that's it. This has been the last session. Thank you.